This video is for lesson 19-2 about a concept called geometric mean. We're going to use that relationship from the previous lesson called the right triangle altitude theorem as the basis for a new geometry concept called geometric mean. Take a look at this drawing right here in the middle of the screen. Isn't this the same situation we had in the last lesson? We had a right triangle with an altitude drawn to the hypotenuse of the original triangle, creating two smaller right triangles. Those are both similar to the original triangle. Now let's look at the sides of these different triangles, and let's create a proportion with those different segments. We could say that x is to t as t is to z. Think about what these things are. X is this length right here. It's the shortest side of the small triangle, or another way to think of it, it is the small piece of the hypotenuse of the original large triangle. What's t? T is the altitude that was drawn in there. Over here, what's z? Z is the other piece of the hypotenuse of that original triangle. So what's going on here is when we can draw an altitude in, we can say that that altitude is the geometric mean between the shorter piece of that original hypotenuse and the longer piece of the original hypotenuse. That idea is shown in this statement here, which is called a corollary to the right triangle altitude theorem. A corollary is an idea that comes directly from a theorem. When an altitude is drawn to the hypotenuse of a right triangle, the length of that altitude is the geometric mean between the segments of the hypotenuse. We're used to arithmetic mean, also called average, where you add two numbers together and divide by 2. Geometric mean is another type of average. What we're saying is, in a picture such as this on the screen, that altitude is the geometric mean of the short piece of that hypotenuse and the longer piece of the hypotenuse. As a proportion, it looks like this statement. This is the short piece, t is the altitude. Over here, t is the altitude, z is the longer piece. The short piece is to the altitude as the altitude is to the longer piece. When I say short piece and longer piece, I'm talking about this length here and this length over here. Because of the different similar triangles in the figure, we could create another proportion, which you see right here. Think about what these are. Again, x is that short piece of that original large triangle. It's also the shortest leg of the small right triangle. U is the hypotenuse of the small right triangle. In the original triangle, it was its short leg. What's the p? P is the hypotenuse of the original largest triangle. Think about what these four things are. We're saying that x, the short piece of the hypotenuse, is to the short leg of the original triangle, as that u is to the hypotenuse of the original triangle. That's shown here in corollary 2. When an altitude is drawn to the hypotenuse of a right triangle, each leg is the geometric mean between the hypotenuse and the part of the hypotenuse adjacent to the leg. I'm going to pause the video for you to add both of these corollaries to a note page, because you're going to want both of these statements when you take a quiz over this topic. Let's try an example problem where these corollaries are useful to us to figure out unknown lengths. Here we have a right triangle, triangle DFE, a large right triangle. Notice that it has a segment drawn from F to G, touching with a 90-degree angle. That's called an altitude. So that is that situation where the right triangle altitude theorem applies. It creates two smaller right triangles that are similar to the original. Not only does the theorem apply, but both of these corollaries apply. So let's figure out x if we're told that y is 9, so we can put 9 where the y is, and we're told that the z is 36. We want to find x. We're going to use the first of the two corollaries. 9 is to the x as x is to the 36. Think about what this proportion has to do with that first corollary statement that you have written out in words. The short piece of the original hypotenuse is to the altitude as the altitude is to the other piece of the original hypotenuse. When you have a proportion and you have the same number in this position as in this position, that number there is called the geometric mean between that number and that number. It's not the same thing as arithmetic mean. It's not the normal average that we're used to, but it is a type of average. Now to find the answer, we can use cross multiplication. So x times x is x squared, and then 9 times 36, which is 324. And then to solve for x, take the square root. So the square root of 324 is 18. We're able to find the length of that altitude. It's 18. The way that we found it was using one of the corollaries from the right triangle altitude theorem. Next, let's work on these, try these problems. It says use that same figure from example A and the corollaries to answer these questions. First thing I'm going to do is redraw that triangle down here in this space so that we can work with it. Here it is. We're told that y is 2 and x is 16 and asked to find z. So let's label those. Now to do this question, let's think about what information we know, where the segments are that we know that information. We have a right triangle, we have an altitude drawn, and we know how long that altitude is. We have a 2 written on the short piece of the original hypotenuse, and we have the letter z written on the other piece of the hypotenuse. We're going to use the first corollary. Here's how it works. The 2 is to the 16 as the 16 is to the z. The 2 is the short piece of the hypotenuse. The 16 is the altitude. Over here, we have that 16 again, and then z is the long part of the hypotenuse. We can solve this with cross multiply. 2 times z equals 16 times 16. 16 times 16 is 256. Now divide both sides by 2 to get z alone. And we get 128. Okay, I'm going to pause the video for you to work on question B by yourself. First thing you need to do is redraw that triangle so that you can label the parts with these numbers that you're given, and also so you can figure out where the unknown segment is that you're asked to find. So here's the drawing with everything filled in. Now let's think about what we have information for and what's missing. 18 is the altitude, y is the small part of the original hypotenuse, 45 is the other part. This is that corollary 1 situation. Y is to the 18 as 18 is to the 45. There's your proportion setup. Now use cross multiply. 45 times y equals 18 times 18. Divide both sides by 45 to get the answer for y. And the result is 7.2. Next, we have some check your understanding questions. Question 5. Explain how to use one of the corollaries to find Jm. Then find Jm. So here we have our triangle. We know some of the numbers. Jm is the altitude. It has the letter x written on it. We have to know which corollary to use. So what's the 12? The 12 is the smallest part of the original hypotenuse. What's the 48? It's the other part of the original hypotenuse. We want to use corollary 1. 12 is to the x as x is to the 48. You could solve that with cross multiply. Now question 6. We have another right triangle where there's an altitude drawn from A to S. In the original right triangle, the hypotenuse is segment EY. That hypotenuse is split up into two pieces. The shorter piece is the ES. The longer part is that SY. Okay, X is 4, so we can label that. Z is 9, we can label that. We're asked to determine T, the altitude. Which corollary do you use? Okay, I hope you chose the first corollary. I'm going to pause the video for you to create your proportion and solve for T. Over here on the right side of the screen is the answer. We have our proportion, and the answer is T equals 6. Now for question B, let's erase the information that we've already labeled and relabel it with what we have here in B. X is 6, T is 12, and we're asked for Z, which is this right here. Which corollary should we use, the first one or the second one? I hope you chose the first corollary. So I'm going to pause the video for you to write your proportion and solve for Z. Over here on the right is the answer. We have our proportion, and then the solution is Z equals 24. We haven't done any examples where you use the second corollary. So let's do one. Take a look at number 7. Explain how to use the two corollaries to find PJ and find PJ. So we have a right triangle. The hypotenuse of that triangle is 34 units. The short side of that original triangle is 15. PJ is an altitude drawn in that triangle. That's what we want to find out. But we can't use corollary 1 to find that altitude because we don't have that original hypotenuse separated into two segments. So corollary 1 is not going to get us anything. What's corollary 2 talking about? Let's go back and look at that. Here it is. When an altitude is drawn to the hypotenuse of a right triangle, that's what we have. Each leg is the geometric mean between the hypotenuse and the part of the hypotenuse adjacent to the leg. Each leg is the geometric mean between the hypotenuse. Do we have a number on a leg? Yes, we do. Do we have the number on the hypotenuse? Yes, we did. The leg is the geometric mean between the hypotenuse and the part of the hypotenuse adjacent to the leg. Let's use that corollary. The leg, the 15, is the geometric mean between the hypotenuse and the part of the hypotenuse adjacent to that leg. So that small part of the hypotenuse is what we're talking about. We don't know what that is. Right now it's just called NJ. We do know the hypotenuse, 34. This is what the proportion looks like that corollary 2 was talking about. The leg of the original triangle, that is the side with the 15, is the geometric mean between the hypotenuse, that's the 34, and this small piece of the hypotenuse. We could now use cross multiply. 34 times NJ equals 15 times 15. Divide by 34 and we'll have the answer for NJ. NJ is 6.6. Now in the original drawing, we can label NJ with 6.6. And if we know the entire hypotenuse is 34, we could subtract 34 minus 6.6 to find out that this part over here is 27.4. Do you remember how we were asked to find PJ, which is the altitude? Now we can do it, because now we have what we need for corollary 1. We have that hypotenuse separated into the two smaller segments. So 6.6 is to PJ as the PJ is to the 27.4. If you don't like having PJ with its name with two letters, you can always put a single variable on it like X, so that in your proportion you're able to put the single letter X instead of putting PJ. You might like that better because you're more used to variables. Now you can use cross multiply. X times X is X squared, and then we have 6.6 times 27.4. This makes X squared equals 180.8, and we can take the square root to get the final answer. It's 13.4. So there is a time where you're going to want to use corollary 2. So in this lesson, we discussed two corollaries of the right triangle altitude theorem, and with these corollaries, we're able to figure out unknown segments in right triangles.